Welcome to the online narrated lectures for CM2101. In week 5, we will begin our discussion of rotational spectroscopy. The reason why we start with rotational spectroscopy is because it is the simplest to understand. In discussing rotational spectroscopy, we do not need to worry about concomitant vibrational and electronic transitions. Rotational transitions occur at much lower energies than that required for vibrational or electronic. So vibrational and electronic transitions will not be excited at the same time as rotational transitions. We will look at the specific setup for a microwave absorption instrument. Remember that the radiation normally associated with transitions between rotational energy levels is in the microwave region of the electromagnetic spectrum. For this reason, rotational spectroscopy is also frequently referred to as microwave spectroscopy. The simplest molecule to discuss in rotational systems is a rigid diatomic, and so that is where we'll start. In nature, many elements have more than one isotope. We will investigate how this will affect rotational spectroscopy. We will then relax the approximation that the molecule is rigid and see how this affects our solution. Polyatomic systems introduce additional complications, and we will discuss some of these. Finally, we will report modern applications of rotational spectroscopy. In part 1, we will look at the instrumentation involved and some of the observations that we will need to explain. However, before we look at the instrumentation and the observations though, you may have asked yourself, why should electromagnetic radiation affect the rotation of a molecule? Now, to be fair, the answer lies in some fairly esoteric quantum calculations, but we can appreciate it using classical physics. Remember that electromagnetic radiation is comprised of an electric field and a magnetic field propagating at right angles to one another. Well, if we place a molecule, say a heteronuclear diatomic, that is one that has a permanent dipole moment, we can see what will happen. The electric field will exert a force on the positive end of the molecule in the opposite direction to the force that it will exert on the negative end of the molecule. This will exert a torque or turning force on the molecule. As the electromagnetic radiation passes over the molecule, we can imagine that the molecule could be forced to rotate at some frequency. Although this explanation is flawed, it does give you an idea of how light and matter can interact and manifest itself as changes in rotation. In particular, this simple model implies that the electromagnetic radiation will excite the rotational levels of a molecule provided it has an electric dipole moment. It can do this because the electromagnetic field can exert a torque on the molecule. You will remember that for microwave and radio frequency radiation we have a tunable monochromatic source. A common microwave source is a klystron, although many modern instruments employ solid-state devices. The klystron still has an advantage over more modern solid-state sources in that they can produce far higher microwave output. The problem with the klystron, though, is that it is a pain to operate and can be quite dangerous. For instance, if you fitted a tube that was too narrow, then the microwave radiation would not be able to propagate down the tube, and in fact the microwave radiation would be reflected back into the klystron and destroy it. It has to be said that rotational spectroscopy is not very popular today, but this might be changing. A few years ago, someone managed to improve upon the old design for a Fourier transform microwave spectroscopy. This would make this spectroscopy a lot easier and faster to conduct, so we will see whether this manifests itself in making rotational spectroscopy more popular. The microwave radiation that comes out of the klystron is sent down a hollow tube made out of copper or silver. The inside of the tube is frequently coated in gold. This tube is acting as a waveguide. You have probably seen an optical fibre down which we can send visible light. That optical fibre is also acting like a waveguide. It prevents loss of radiation along the path down the optical fibre. The central section of the tube is separated from the rest of the instrument by mica windows. Mica is a silicate mineral that forms wonderful laminar sheets. It is useful for us in constructing this instrument because mica is transparent to microwave radiation. The central section can then be evacuated using a vacuum pump, and the sample that we are interested in can be introduced as a gas at low pressure. The detector is simply a radio receiver or crystal detector. We can then pass microwave radiation from, say, 0.1 to 100 wave numbers through our sample and collect the spectrum. Well, let's suppose that we introduce a diatomic gas. Let's say we have dioxygen or carbon monoxide. What will we observe? Well, for dioxygen, we will see no spectral lines. But for carbon monoxide, we do see spectral lines. Does this mean that dioxygen molecules do not rotate? No. Dioxygen molecules are rotating, and indeed dioxygen molecules are constantly changing rotational energy through collisions. These observations are telling us that microwave radiation can be used to change the rotational state of carbon monoxide molecules, but not for dioxygen molecules. Here is a typical spectrum that we might record for carbon monoxide. This figure comes from Hollis's modern spectroscopy. What features do you notice? I hope the first thing that you notice is that the spectral lines appear to be evenly separated. I should also point out here that we are measuring transmission and not abundance. So when the transmission is small, it means that the sample is doing a lot of absorbing. There is one other feature that is apparent. There appears to be a second set of lines and much smaller intensities which are slightly closer together. This is not noise. For one thing, it is occurring periodically. What is this due to? In fact, it is due to the presence of carbon-13 monoxide, which amounts to approximately 1.3% of all the carbon present. In a sense, we have two overlapping spectra here, one due to carbon-12 monoxide and one due to carbon-13 monoxide. The ratio of the intensities is in fact one of the ways we know the relative abundances of these isotopes. The even separation of the spectral lines is confirmed in the following table. Again, this comes from Hollis. The lines, you'll notice, are approximately 3.85 wave numbers apart. The even separation of the spectral lines is confirmed in this table. The lines are approximately 3.85 wave numbers apart. Note that this table records lines earlier in the spectrum than those seen in the spectrum on the previous slide. The first line seen in the spectrum on the previous slide was at 15.38 wave numbers. This is simply due to the range chosen to be presented and not because the data wasn't available. The spectrum also shows only a slight change in relative intensity over the spectral range measured. I want to stress one further point. Rotational spectroscopy can be very accurate. The numbers in this table are being reported to 7 significant figures. This is because they are accurate to a very high fidelity. The information that we can glean from this data will also be very accurate because of this. One of the reasons why this spectrum has so little broadening is because this spectrum was recorded at some 40 to 50 Kelvin. This was clearly not done in the laboratory, but instead this measurement comes from the star-forming regions of an interstellar dust cloud. We can use microwave spectroscopy to identify molecules in space, and we do this all the time. In fact, one of the more interesting molecules that was recently identified in an interstellar dust cloud was ethyl alcohol. That's the same kind of alcohol that you find in beer. In fact, they were able to estimate the amount of alcohol in the interstellar dust cloud, and they estimated it would be enough to make 400 trillion glasses of beer. Other interesting molecules that we have seen in interstellar dust clouds are amino acids, the very building blocks of life. So we have 3 observations to account for. First, there is no rotational spectrum for dioxygen, a homonuclear diatomic. Second, there is a rotational spectrum for carbon monoxide, a heteronuclear diatomic. And third, the spectrum consists of evenly spaced lines with only slight changes in relative intensities. How can we account for these observations? To account for these observations, we need to solve the Schrödinger equation. Fortunately, I do not go into any real detail about the solution, but I do want to guide you through how it is done. We will be concentrating on the solutions. To solve the Schrödinger equation, we need the Hamiltonian for a rotating system. You may remember from school that rotational energies were related to rotational speeds and moments of inertia. I want to spend a little bit of time discussing moments of inertia. Well, what is it, you may ask? Well, it is simply the resistance of a rotating body to a change in its rotational energy. It is directly analogous to mass in linear motion. Mass represents the resistance of a linear moving body to a change in its linear motion. We will see that this analogy will help us to construct the Hamiltonian for a rotating system. Here is a graphic of two cylindrical steel bars of the same mass being rotated. One is being rotated around the centre of the cylinder, while the other is more of an end-over-end rotation. Intuitively, the first steel bar is going to be much easier to spin, and the reason why it is much easier to spin is that its moment of inertia is smaller. That is, its resistance to rotational change is much smaller. The second one, however, is much more difficult to spin at the same rotational speed as the first one because its moment of inertia is a lot larger. This is intuitive, but I agree that rotational motion is not as easy to understand as linear motion. Let's compare rotational motion to linear motion. Here we have linear motion. We are going to consider two concepts in linear motion. The first is linear velocity, which tells us the speed and direction this ball is rolling across the surface. The second concept that you are familiar with is mass. This ball has a mass m, which means its linear momentum will be mass times the velocity v. Now what about circular motion or rotational motion? If I've got a particle that is moving around this ring, it will have an angular velocity omega. Its angular momentum, though, rather than its linear momentum, will also have a magnitude and direction, but its direction is defined to be perpendicular to the plane in which it is moving. What I want to show you is what the angular momentum is equal to in terms of the angular velocity and its moment of inertia. So what is moment of inertia? Here is a randomly shaped body. I'm going to be assuming that it's rotating around the z-axis here. So what I want to know is what is the moment of inertia around the axis of rotation. I'm going to set it off with a certain angular velocity omega, and then I'm going to look at a particle I, that is a perpendicular distance r sub I away from the z-axis. This particle is moving at the same angular velocity as every other particle in the body because every particle needs to sweep out the same number of degrees per second, because if they weren't, the shape itself would fall apart. So all the particles are moving with the same angular velocity, but they have different instantaneous linear velocities. The linear velocity of a certain particle is the perpendicular distance times the angular velocity. So the particles which are closer to the axis have small instantaneous linear velocities, but the particles which are further away have much faster instantaneous linear velocities. If I know the linear velocity of a particle, I can also say something about the kinetic energy of that particle. So the kinetic energy of the particle is a half mv squared, and I can substitute v for the angular velocity, so that I get a half mr squared omega squared. If that is the kinetic energy of each particle, then what would be the total kinetic energy of the entire body? All I need to do is sum up all the kinetic energies of the particles in the body. So if I know the masses of each particle, mi, then I can sum up the kinetic energies of all the particles by multiplying these masses by half the distance from the axis of rotation ri and by the angular velocity squared. We can take the omega squared outside because it's the same for every particle. What we will be left with is a half times the sum of the mr squared terms for all of the particles. This sum is the moment of inertia. So now the equation for total kinetic energy is equal to a half times the moment of inertia I times omega squared. The form of that equation is quite familiar for kinetic energy. The kinetic energy of a linear moving body is just a half mv squared, whereas the kinetic energy of a rotating body is a half I omega squared. So when we make the transformation from linear motion to rotating motion, my linear velocity v gets changed into angular velocity omega, and my resistance to linear motion mass gets converted to my resistance to angular motion I. So you can see that it is directly analogous. So the resistance of the rotating body to a change in its rotation motion about a given axis is my moment of inertia. We can see, of course, that the moment of inertia is axis dependent. So if I go back to my rotating steel rods, we can see why the first rod has a smaller moment of inertia and why it is thus much easier to rotate. We can see that each particle is much closer to the rotational axis in the rod on the left than in the rod on the right. So the average distance in the first configuration is much smaller than in the second, so the moment of inertia is smaller even though they are identical rods. The moment of inertia is dependent on the choice of the rotational axis. There is another thing I need to explain about moment of inertia. Just like in linear motion, where there is conservation of momentum, in rotational motion we have conservation of angular momentum. This is best illustrated in a video. That was a video of Natalia Kanunikova, who set a world record for the fastest spin on ice skates. At her peak there, she was rotating about 5 times per second. But why did her rotational velocity increase? What has she done? She has pulled her legs in closer to her body. But why has that changed her rotational velocity? Well, in doing this, she has changed her moment of inertia. When her arms and legs are out, there is more body mass further away from the rotational axis, and so she has a larger moment of inertia. When her arms are tucked in, she has a much smaller moment of inertia. Now, because angular momentum is conserved, the initial angular momentum is equal to the final angular momentum. And so because the moment of inertia gets smaller, the angular velocity gets bigger. And thus, she's able to spin incredibly quickly. We will now try to model the diatomic molecule. The simplest model of a diatomic molecule is to assume that the two atoms are connected by a massless rigid bond. The mass of each atom is in the center of each atom. There is no mass in between and the bond length doesn't change. These assumptions make the mathematics easier. But even with these assumptions, many of the features in the rotational spectrum of a diatomic are explained. So here we've got end over end rotation. If we assume that the molecule is rotating in this plane like so, with the atoms having mass m1 and m2, then the molecule will be rotating around the center of mass. Now it is quite easy to think about where the center of mass is. If you have masses which are equal, the center of mass will be equidistant between the two atoms. But where is the center of mass when the atoms have different masses? Let's have a look at this situation and see if we can justify what is happening. If the bond length is r, that's capital R, and we assume that mass m1 is a distance r1 from the center of mass, and that mass m2 is a distance r2 away from the center of mass, how long is r1 compared to the bond length, and how long is r2 compared to the bond length? Well, the center of mass is defined by this equation, because the moment associated with mass m1 around the centre is going to be m1 times r1, and the moment associated with mass m2 is going to be m2 r2. If we had a fulcrum at the centre of mass, then it would not rotate in any particular direction. This occurs when we have m1 times r1 is equal to m2 times r2. In terms of the moment of inertia, we have only two particles to consider. So this sum can be broken down into the component for particle 1 and the component for particle 2. We can use these equations to define the moment of inertia for a diatomic molecule in terms of the bond length r. With a simple mathematical manipulation, we are going to introduce the concept of reduced mass. The moment of inertia about the centre of mass depends on the rotational axis. Remember that the rotational axis is always through the centre of mass. We already knew the expression for moment of inertia, but now we also know that m1 times r1 is equal to m2 times r2. Noting that the bond length r is equal to r1 plus r2, and with a little bit of manipulation, I can write r1 purely in terms of the bond length. There is a similar expression for r2. If we then substitute these expressions for r1 and r2 in terms of the bond length into the expression for the moment of inertia, you'll find that the moment of inertia is equal to m1 times m2 over m1 plus m2, all times the bond length squared. And we call m1 times m2 over m1 plus m2 the reduced mass, which is given the symbol mu. So the moment of inertia for a diatomic system around the centre of mass is simply the reduced mass times the bond length squared. Let's have a look at what this means in terms of rotational motion. What kind of transformation have I done? One way of looking at this is that I started off with two masses, where one mass is r1 away from the rotational axis and the other is r2 away from the rotational axis. And I ended up with a moment of inertia equation that has one mass, the reduced mass, a distance r, which is the bond length, away from the rotational axis. Mathematically, the two-mass system is identical to the reduced mass system. This mathematical transformation simplifies our equations, which is why we did it. We're going to calculate the reduced mass for diatomics quite a lot, but there is an issue here with regard to isotopes. Which masses should we employ? For instance, what is the reduced mass of N2 dinitrogen? How would I calculate it? Where would you go to look up the reduced mass of dinitrogen? All we really need is the mass of the nitrogen atom. If I go to a periodic table, it will tell me that the relative atomic mass of a nitrogen atom is 14.007 atomic units. Could I use that? We saw before what happens when we have carbon-12 and carbon-13 monoxide. They gave rise to overlapping spectra. They didn't lead to an average spectrum. This means that we have to use the isotopic mass and not the relative mass of all the isotopes. This is because the relative mass is an average in terms of the relative abundances of all the isotopes. So if we have nitrogen-14, we would use 14.003 atomic units, and if it was nitrogen-15, it would be 15.000. It just so happens that about 1% is found as nitrogen-15. This would make a difference in terms of where the spectral lines would occur, as we saw for carbon monoxide. So it is important, and in fact if our instrument was good enough, I would see the two overlapping spectra between the nitrogen-14 diatomic and perhaps a small amount of nitrogen-14 nitrogen-15 diatomic. But I've tricked you here. In fact, of course, we wouldn't see a spectrum for dinitrogen because it's homonuclear. It doesn't have a dipole moment. But we can see this effect for something like carbon monoxide. The bottom line here is that you cannot use the relative atomic masses. You must use the isotopic masses. This is the end of part 1 of this week's online lecture. Please continue on to part 2.